This is chapter 2, motion in one dimension, and here basically we need to understand the equations and take it from there. The first one is the initial velocity, v naught. The second one is the final velocity, vf. Final velocity, vf. A is the acceleration. Delta t is the time that has elapsed, and delta x is the displacement. So these are the five quantities, and initial velocity and final velocity both are measured in meter per second. Acceleration, the unit is meter per second squared. Time is in seconds, and displacement is in meters. So those are the units. Now let us take a look at those equations. By definition, acceleration is change in velocity divided by time. So we have the first equation, v final minus v initial by time. And the second equation, you can find the displacement by using the formula v naught plus vf by 2 times t. That's the second one. And the third, displacement is v naught t plus 1/2 at squared. The final equation is v final squared is equal to v initial squared plus 2a delta x. And if you notice, each of these four equations only has four terms each. And so when you read a problem, you need to figure out which one of the equations is to be used by noting down what is given. Let's practice a few and then you will understand. Now, here is a question that's coming up. Let's say that an object is just dropped from a certain height. Just dropped, you let go. So the initial velocity is 0. And since it's falling under the action of gravity, the acceleration is negative 9.8 meter per second squared. Now, why is it negative? Because it's going down. Now, acceleration due to gravity is always going to be negative 9.8 meter per second squared because the gravitational force is downwards. So even when you throw an object up, its acceleration due to gravity is down. The initial velocity is 0, the acceleration is negative 9.8 meter per second squared. So we can find the displacement after a particular time, let's say 2 seconds. Now when you look at these quantities, you understand that all these four quantities come into play in this equation. And so you substitute into that equation, and the first term, which is v naught t, becomes 0 because v naught is 0. And so you only have 1/2 times negative 9.8 times 2 squared, which is 4. And so you get, when you calculate, negative 19.6 meter. So that means this object has moved negative 19.6 meter in 2 seconds. What does the negative show again? That the displacement is downwards. That's what the negative shows of 10 meter per second. So now that's the diagram. The object is thrown vertically up, and now the initial velocity is not negative 10, but it's positive 10. Why is it positive 10? Because it's thrown up, and up is positive. So now we have the initial velocity as 10 meter per second. Acceleration is again negative. Remember, it's always negative 9.8. And then we can find the displacement in the first 2 seconds. Alright, so the same equation is used. And when you plug it in, you get 10 times 2 plus 1/2 times negative 9.8 times 2 squared, which is going to give a real small displacement as 0.4 meter. Now what does it mean? Look at that. So you throw it from here vertically up, it goes up, and in 2 seconds it reaches somewhere here. So the displacement is this much. See, that's the displacement. The displacement is small, it's positive zero point 0.4 meter. I hope you understand that. Here is another question. A race car completes a lap of 1000 meters with an average speed of 200 km per hour. If the average speed on the first half of the track was 225 km per hour, what was its average speed on the second half? So average speed means total distance by total time. The average speed is given as 200 km per hour, but the race car moves at 225 km per hour in the first half, and in the second half you're asked to find the average speed. So here is how we do it. That's the lap, assuming that it's in a straight line, and then we got to have it in kilometers, so 0.5 half, the time taken should be 0.5 divided by the average speed there, which is 225. So that's what I'm doing. Distance by speed gives 0.022 hours. Now for the second half, similarly, the time should be the same distance divided by x, because we do not know the average speed. And then we use the formula for average speed, which is total distance by total time. The total distance in this case is 1 kilometer, so that will be 200 km per hour, which is the average speed given, is 1 divided by 0.022 plus 0.5 by x. Now why? Because that's the total time. The time for the first half plus the time for the second half. So you have an equation from which we have to solve for the value of x. Okay, so let's do that. I'm cross multiplying, so 200 times 0.022, 0.0022 I mean, gives that number, and then 200 times 0.5 by x gives 100 by x is equal to 1. Now rearrange that. Basically I took 0.4444 to the other side, became negative, and then difference is that, and then x is 100 divided by 0.555, which is 180 km per hour. So that brings us to the last question. Here an Olympic runner starts from rest and has an acceleration of 2.0 meter per second squared for 3.5 seconds, and then has zero acceleration for the remainder of the race. So in a race they try to have maximum acceleration and then try to maintain that. So for 3.5 seconds this is the acceleration, and then there is no acceleration, which means the runner keeps running at the same speed for the remainder of the race. Find the runner's speed after 2.0 seconds and at the end of the race. So what do we have here? What is the initial velocity? Surely every runner starts from rest, so the initial velocity is 0. The acceleration is given 2.0 meter per second squared. Time is 2.0 seconds because we're asked to find the speed after 2.0 seconds. And then when you look at these terms, you see that the formula to be used is V final is equal to V initial plus AT. V initial is 0, so 2 times 2, that's the acceleration, that's the time, which gives us 4.0 meter per second. In the second part, we are asked to find the runner's speed at the end of the race. The time is not specified, but we do know that after 3.5 seconds, the runner's speed does not change. So what we will do is, we'll find the speed at the end of 3.5 seconds. That will be the speed at the end of the race. That makes sense? So I'm writing it down. The speed at the end of the race is exactly the same as the speed after 3.5 seconds. So all we got to do is find the final speed after 3.5 seconds using the same formula, which gives us 7.0 meter per second, because you have 2 times 3.5. So I hope this is of help to work out the problems. But remember, you got to watch the lecture on this chapter, read the textbook in order to be able to do the homework and to do well on the test. Good luck.